What's up, dudes? Hope the break went well or is going well or whatever you want to say there. Um, Obviously, you've seen your midterm grades. Skip that, all that. This is just making the video longer. So, our new unit is really an extension of our current electricity unit. Really, this kind of wraps up our greater, what we call E&M unit, electricity and magnetism. This section of it is on magnetism by itself and what I call electromagnetic interactions. Some of the way coolest physics that we'll see all year, in my opinion. So let's start off with the super duper basics. Can we do this? Yeah, good. The super duper basics, just plain old magnetism and magnetic fields. Well, magnetic fields exist in lots of places. All right, and I should back up a little bit even before that. We've talked about fields. There are three kinds of fields, really. I don't know, maybe four. But there are, for sure, gravitational fields. We spent time talking about those. There are electric fields. We've spent time talking about those. There are magnetic fields. Okay? And one place, certainly, that magnetic fields exist is near magnets. Duh. Right? And particularly something simple we call a bar magnet. Okay, we have lots of bar magnets. I'll get some out on Monday when you're here and show you these things. But what we can do to look at magnetic fields is you can use a magnetic compass. So you've seen little compasses before, right? A little circle. They have a little a thing, a little indicator that points somewhere, right? For ours, they point toward magnetic north. Well, really, compasses point in direction of magnetic field lines. So if you put this compass around this thing is our bar magnet. If you put the compass in lots of places around the bar magnet, what you'll see is that the field looks something like this. Well, it points like away from this end, and it points toward this end, and here it points away like this, and that line actually can curl around just like this, and there's one here that would look like that, and one here that looks like this, and there's a symmetry around here. So these fields, a magnetic field near a bar magnet, can look something like that. I'll put arrows on here. Okay? So when I slide this compass around to all these different locations, well, right here, the needle points that way. Right here, the needle points to the left. Right here, the needle points up. Right here, the needle points right. So we can literally, and we'll do this, slide a compass around a bunch of locations around a magnet, and we can look at the field lines. All right, the field lines actually, well, I'll get to that in a minute. What it turns out, when we do this, you'll see that, fine, is that magnetic fields point toward magnetic south. And they point away from magnetic north. All right, so that's a big deal for us. Just like we talked about the convention by which we define what direction electric fields point. Well, electric fields, they point in the direction of a force at a positive charge or field, blah, blah, blah. But we say that, electric fields point away from positive charges. Electric fields point toward negative charges. Well, magnetic fields point away from north. Magnetic north. And they point toward magnetic south. Right? That's the definition of what direction magnetic fields point. Any questions? Good. Now, the one thing I will tell you is that these lines, magnetic field lines, actually are continuous. So inside a magnet, we actually change that convention, and the lines point inside the magnet. They point from, it's still the same. From north. No, sorry. Inside the magnet, it's from south to north. Okay. Outside the magnet, from north to south. Okay? But this is the big deal. Just worry about outside. Now, that tells you something, like we said, we can use magnetic compasses. We use them to navigate, right? So, if we look at the magnetic field around the Earth, well, the compass tells us how to get to Santa's house, right? It tells us how to get up here. Because the needle, if we put the compass here, the needle points that way. We put the compass here, the needle points that way. Put the compass here, needle points that way. Which means that the field around the Earth, well, is a lot like the field near a bar magnet, except it looks like this. It comes out of here, it comes, well, like out of this and comes up like that and then points down in like this. And then out of here and comes around like that and points down here. And it comes out of here. And this is in front of the Earth, right? In front of the Earth. It would do the same thing behind the Earth, right? These are all magnetic field lines, pointing, well, from south to north. But I thought we said they point from north to south. Well, that tells us something interesting about the magnetic field around the Earth, or really about the Earth itself. What it tells us is that if the magnetic field lines point this way, that means that this is a magnetic south. And this is a magnetic north. We get that? Just like over here, right? Field lines point away from magnetic north. They point toward magnetic south. So our geographic north is actually a magnetic south pole. Interesting. I say. Interesting. Next. Blank page. Now, what makes things magnetic or non-magnetic? Well, the deal is that in everything there are little tiny what we call magnetic domains, right? And we could say that the domains are kind of like, well, imagine a bunch of little bar magnets inside anything, right? And the bar magnets, well, just like a compass. I mean, a magnetic compass, I guess I'll leave this slide up. A magnetic compass is nothing more than, a thing with a, well, how about I do this? It's a, oh boy, come on. It's a, good. It's a thing like this, a little tray with like a pin in the middle, and on that pin balances a little bar magnet. It's just balanced on there, and it's a magnet, right? And so it is affected by magnetic fields. So it's kind of like, imagine there are a bunch of little compasses in this non-magnetic material. Well, what you get are little magnetic domains that point in lots of different directions, in very random directions, and entirely random directions, actually. All right, there's all these little, what we call magnetic domains that point in lots of random directions. No order to them, okay? But in a magnetic material, all these little magnetic domains end up pointing in the same direction. All right? You get the idea. So we say here that magnetic domains are aligned. All right? Where do these magnetic domains come from? We'll get to that. Okay? A couple of very important, very standard fields you have to get used to are the fields near to the ends of two bar magnets. This, of course, assumes that over here there's a north, and that over here somewhere there's a south. Okay? This is just saying, here's just the end of it. So the field points, well, away from north and points toward south. Okay, this is what we call a uniform. Well, what I should say is that uniform B, and B means magnetic field. B-U-I-B, I don't know. M means mass or something. All right, and it's measured, B is measured in Teslas. So we'll call that capital T. Okay? You'll really only deal with these magnetic fields. I mean, the field here would look, kind of like this field near two positive charges, right? Where the lines curl away from each other. But we don't ever deal with those in many practical well, I shouldn't say that. We don't deal with them in any problems that we solve. There's certainly practical applications for having magnets aligned like that. Right? Other big thing about a magnet, you take this magnet here, and well, let's see, this would be the south over here. This would be the north over here. You chop it in half right there. Well, you don't end up with a north pole and a south pole. All right, that's something about magnets. There's no such thing, well, naturally occurring really, as what we call a magnetic monopole. Magnets always occur as dipoles, two poles. There's always a north and a south together. Right? We can have a proton by itself. We can have electrons by themselves. All right, but we never get a north by itself. All right. Another big thing that I should make sure I say, we're talking about, well, magnetic fields point away from positive, away from north towards south. That does not mean that north is positive and south is negative. They are completely different things. All right. Don't get that in your head. Well, because the field points like that, it means north is a positive. North is not a charge. All right. South is not a charge. All right. Completely different phenomena. Okay. So there's that. Yeah. I want to sort of forget. No, I don't. No, I don't. Yeah. Good. So yeah. Why are magnetic things magnetic? Well, because these magnetic domain things are all lined up. All right. Well, why does that happen? Well, that really gets to why another sort of point about why things are magnetic. Well, everything's kind of magnetic. Everything has these magnetic domains in them. All right. But and only some of the things are the magnetic domains lined up. All right. Well, where do these magnetic domains come from? They come from moving charges. All magnetic effects come from the fact that charge moves, because moving charge creates magnetic field. That's a big deal. That's our first electromagnetic interaction. Plain old moving charge creates magnetic field. All right. Now, we're going to sort of have to come back to this whole idea. We'll do that soon enough as to answer the question. So what? Why does that make things magnetic? But here's the deal. We want to deal with this idea pretty strongly for a few slides. All right. The fact that moving charge makes magnetic field. Perhaps one of the most important things from this video. Moving charge creates magnetic field. And the magnetic field around a current carrying wire, for example, you can figure out the direction of it by using what's called a right-hand rule. You're going to learn lots of right-hand rules in this unit. There are. I've told you this. I think some of you. There's a quiz you'll take where you won't use a calculator at all to find answers for things. You will use your right hand only, just your right hand, and you'll be pointing your hand in different directions and curling your fingers like you see in this diagram. If we know the direction of current, electrical current, and ding, 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 this means conventional current. If you don't know what conventional current is, you need to. I'll just tell you, conventional current is the direction of the direction of free positive charge flow. All right, you got to know that. So if we know the direction of conventional current, what we do is we put our thumb in that direction. So this thing is a wire. And we're saying that somewhere down here there's like a positive and somewhere up here there's a negative. So conventional current would be the direction that a positive charge would go. That positive charge would go this way. So that's the direction of our conventional current. So we put our thumb in that direction. If we want to look at the magnetic field, we take our fingers and we wrap it around the wire. And our fingers point at any location in the direction of magnetic field. Let's say, in this example here, that current, conventional current, goes that way. Well, 4 places we'll talk about the direction of magnetic field. One of them is, I don't know, let's say here's location 1, left of wire. Here's location 2. Right of wire. Location 3 and 4 are hard to draw because 3 is behind the wire and 4 is in front of it. Those are the 4 places we'll talk about, or we'll be asked to find the direction of the field. All right, so you have to sort of, this is so hard to do over a video, you can't see what I'm doing, but you know, to find the direction of the field at location 1, and again, this is real important, it's called the right-hand rule, sure. For you people that are right-handed, you're going to want to write W-R-I-T-E with your right hand and try to do things with your left hand. Don't do that. Put your pencil down. Take your right hand. So I have my right thumb pointing directly upward in the direction of that current. All right? If I wrapped my fingers around this wire, well, I can't get it. I'm trying to jam my fingers through the board. I can't do it. But if they curled to where location 1 is, I'm doing it even though you can't see me. At location 1, my fingers would point, would point out of the page. Get that? It's like if you would, physically, jam your fingers through your paper at location 2, because at location 2, they point into the page. That's me at location 2 trying to jam my fingers, curl my fingers right through the page. That means my fingers point into the page. Well, by the time they got around to location 1, they'd be trying to push right out of the page. All right, now behind the wire, it's a little easier. At what we're calling location 3, behind the wire, I can't even, I can't draw it, but it's like, it's like back here somewhere. Behind the wire, the magnetic field points to your left. Make sense? If you don't dig it, hold a pencil right in front of you in your left hand and orient it just like this wire is, right? Just put your right thumb right on that pencil pointing upward. Behind the pencil, you can see that your fingers, the tips of your fingers, when they get behind the pencil, will be pointing to your left. Make sense? Now keep your fingers wrapping around. Again, I have a pencil pointing straight up in the air. I have my right thumb right along that pencil in the direction of current. As my fingers get around to the front of the wire, my fingertips are pointing to the right. So in front of the wire, B points right. This is hard to do without having you sit here and watch, but we're going to keep going. Okay? Okay so far? All right. Now, to talk a little bit more about directions, we're going to use some symbols. We're going to try this again. And so, like, if we look at, say, I don't know, let's make current this way. If we look here, above the wire, what's the direction of the magnetic field? Well, again, since this is the direction of conventional current, we take our right thumb and point it to the left. Above the wire, here's my fingers trying to jam into the page. Well, into the page, we use a symbol for that. And to do it, I think about this arrow, the arrow of physics. All right, into the page. If this was right here, if this arrow was shot away from me, shot into the page, what I would see is, well, the back of the arrowhead here and the back of the fins here. So what I see is this symbol. There's the arrowhead, here's the outline of that arrowhead, and here's those fins. That symbol in physics means into the page. So above the wire, because my fingers were trying to poke into the page, we use that symbol to represent the magnetic field there. So I'm just going to even write it. B here is into the page. Below the wire here, here's where my fingers would be trying to come out of the page, right? Out of the page. If this arrow was shot at us, here's what we'd see. The outline of the arrowhead and the tip of the arrow. All right? So that symbol means out of the page. The field's coming right at us. Now, in front of the wire, we can actually do this one, right? So here's my fingers trying to jam into the page above the wire. Well, let's go behind the wire first. Behind the wire, my fingers would point down that way. front of the wire, they'd come out of the page below the wire, and then they'd be pointing upward. Because I could draw, I mean, if I really wanted to, I could draw the field, I don't know, sort of like this. Let's see, out of the page up here, and yeah, the magnetic field really points, it looks like that, all right? So if we look, you know, it is a nice continuous loop around this wire, but we'll talk about it at these 4 different locations. Okay? Okay. Now, oh wait, hang on. We should do this one first. No, yes. Let's do this one first. Now, here we don't care about anything quantitative at all. We just care about directions of stuff. All right, I'm going to do this. You're going to do this. I'm going to look at 3 different locations. I'm going to look at here, here, and here, what the direction of the field is, or what the direction of the net field is. Because now we have multiple currents. All right, so what I have to do is look at, well, for this one, at location A, what field does the green current make at location A? All right, well, the current points upward, or is flowing upward. That means my right thumb goes upward. At location A, my fingers would be trying to poke out of the page. And out of the page looks like that. So there's B1. Okay? Now, at location A, if we look at the red current that goes this way, we would put our right thumb downward. And then at location A, my big long fingers would be trying to poke into the page there if I keep my right thumb pointing downward. So that means that B2 out here would point into the page. Make sense? Now in the middle at location B, let's see. Well, if B1 over here is out of the page, B2 over here, B1 over here must be into the page. There's B1, right? My right thumb is going up because current's going up. Here are my fingers trying to jam themselves into the page there. Therefore, B1 is into the page. All right? Now, if we go right thumb down now, because I2 is down, well, I put my right thumb downward. Here's my fingers again at location B trying to jam into the page. So B1 here, B2 here is also into the page. Okay? See if you can convince yourself that over here at location C, B1 looks like this, and B2 looks like this. Now, what we're going to do is say, well, the net magnetic field is going to be, well, one points in, one points out. Or sorry, this one points out, that one points in. Right? So what we have to do is come up with a sign convention. You pick one. All right? I'm just going to say that here, positive is, I don't know, in. How about that? All right? Well, since B2 is in, I'd call that positive. B1 is out, and call that negative. Here, they're both in. B1 plus B2. Here, B1 is in, and B2 is out. So notice over here, we have B2 minus B1. Here we have B1 minus B2, because the directions of the fields have changed. Ooh, phone call, must be Shanks. Hang on. Dr. Warner. It's Shanks. He's breathing heavily like a weirdo. I'm making a video. I gotta go. Still recording. What a weirdo. All right, so here's what you do. I want you to tell me here, A, B, C, and D, how you would express the net field, just like that, just like this, right? Is it B2 minus B1, B1 plus B2? And let's use this convention. Why don't we say that positive here is out? Fair enough? That's your job. 4 expressions for magnetic field, net field that look like that. Good? Good. Where are we at here? 25 minutes. Let's keep going. Yes. Continuing. Good. Now, here's a nice little multiple choice. No, wait a minute. Well, for this one, wait a minute. Did I skip something? Oh, I did. I skipped this one. Yeah, dummy. All right, so I skipped this page. I can hear you. You're saying, why did you skip this? Sure. Now, we want to be able to quantify magnetic field. All right? Write an expression for the strength of magnetic field. Well, the strength of the magnetic, where'd you go? Strength of magnetic field at any location depends on 2 things. Well, one, can you guess? Come on, take a guess. Pause, maybe take a guess. Super. Well, it depends on 2 things. One is the strength of current. And the relationship is the stronger the current, the bigger the magnetic field. Hopefully that makes sense with your intuition. The second one is distance from the wire. And that goes as B is inversely proportional to the separation, or to the distance from the wire. All right, the farther away you are from the wire, the weaker the field gets. All right, and so we write this expression that B is I over R. Well, hang on. Come on, move. Good. I over R. But we got to do some things, to make the numbers work out, and some things to make the units work out. So we do that. Mu naught I over 2 pi R, where mu naught I is called the permeability of free space. Remember that epsilon naught? We said that K is 1 over 4 pi epsilon naught. Epsilon naught is called the permittivity of free space. This is the permeability of free space. And mu naught is equal to, this is in that reference of yours, mu naught 4 pi times 10 to the negative 7th. And if you solve this expression for mu naught, you get B times 2 pi R over I, right? So that means that the units must be Teslas, meters over amps. Fair enough? Why the 2 pi's and the 4 pi's stuff? It comes from some integration, from some calculus stuff. I will leave it at that. Okay? So there's an expression for the strength of magnetic fields if you know, well, a relationship between magnetic field strength, current in a wire, and distance from the wire. Okay? Well, we could, if we wanted, substitute those expressions in for our B's here. Okay? I'll sort of leave it as just B's now, right? We could write this B1. I just said I wasn't going to do it, but now I'm going to do it. We could write it as mu naught I1 over R1 minus mu naught I2 over R2, right? Where this would be over here, this would be R1, and this would be R2. You get me? Fair enough? So here, we're actually going to do that for this 2 wires carrying currents I2. Yeah, I want you to answer this. Bring me your answer. And let's write an expression for the magnitude of the net field at locations A and B. So at location A, All right, what I would do is say, let's see, the field from wire 1, right? The current goes this way, right thumb is that way. Here's my fingers trying to jam into the board. Field up here looks like that. Well, field from B2, same thing. There's my fingers trying to jam into the board up there. Here's B2. So at location A, I'd say that the net field is B1 plus B2. They both point in. I'll call in positive. Fine. Okay, so we're going to write this as B1 mu naught I1 over R1 plus B2 mu naught I2 over R2. Okay? Now, if you notice in our diagram, we have these separations. So at point A, let's see, distance R1 is just R. Mu naught I1 over R. Distance R2, mu naught I2. Distance R2 is from here to here. So that's 2, whoops, I should do a plus, over 2R. Okay? You can do some algebra if you'd like. So that would be 2 mu naught I1 over 2R plus mu naught I2 over 2R. Or then we can, put all this stuff in the top because we have common denominators. So I'm going to do this mu naught 2I1 plus I2 over 2R. There's an expression for the net field at location A. Okay, at location B, well, let's see. Field from the green, right thumb points to the left. At location B, this one looks like this. At location B, the one from I2, well, here's my fingers trying to jam into the board, looks like that. So that means that the net field is, let's call it B2 minus B1, or mu naught I2 over R2 minus mu naught I1 over R1. I'm making my mu's weird. We know they look like that. I keep doing them like this. They don't look like that. And mu, I did it again. Mu naught I2. Well, R2 is, notice, these are separated by R. This distance is R over 2. So if this is divided by R over 2, then we end up with that. Minus 2 mu naught I1 over R. Okay, so that turns into, let's see, well, 2 mu naught I2 minus I1 over R. And if these two currents are the same current, of course, the net field in the middle of them is going to be nothing. All right? But the net field depends on how strong each of one of those currents is. Okay? I think that's it, folks. Nope, not. Yep. Let's, you. No. Yes, you. Do it. I tell you where point P is. You find me an answer. You want answers? I think I'm entitled to. You want answers? I want the truth. You can't handle the truth. Do the question. Enjoy the rest of your break. See you, folks.